So for the first session of today, it is my great pleasure to present what we have called snapshots of KIPAC research. And we have a selection of 9 short talks for you today from a range of KIPAC members, a lot of graduate students and early postdocs as well. And we are really excited to hear about just the breadth of research that we have going on here at KIPAC. So for our first talk today, it is my pleasure to welcome from the solar physics group, Shea Hess-Webber, who is going to tell us a little bit about her research and the work that's going on in solar physics here at Stanford. So take it away, Shea.
Okay, cool. All right, so this is going to be a bit of a different talk than I think what everyone's been hearing so far this week. It's locally much closer in space and time. We're going to be talking about the sun. This is work that I've done with a lot of different people, some who aren't even actually listed here that were on the original project, lots of different funding institutions involved, lots of different collaborating institutions involved. But so we're going to be talking about trying to determine what the magnetic flux is on the side of the sun that we cannot see at any given time. All right, so firstly, hopefully I don't need to do too much to convince you all of why we care. I mean, I care because it's just fun, cool science, but why should you all care? So probably most of you in the room realize that the sun is a star. That means that it's highly relevant to astrophysics. There are corollaries throughout the universe in terms of other stars with magnetic cycles. It makes a difference in terms of detecting exoplanets, especially through like transiting. I've been talking a lot to folks lately about MHD implications between what we're doing researching the sun versus, for example, black holes and MHD modeling around black holes, different magnetic dynamo scenarios. So astrophysically, it's very interesting and we can actually see what we're looking at. So that makes it pretty exciting. It's also a ready-made plasma physics laboratory with a lot of physics that or the environment that we just can't reproduce in a lab. So that makes it pretty exciting. But what I particularly want to talk to you about today is implications in terms of space weather. If I was going to be there in person, I was going to poll the room to see who of all of you identifies as using technology. I would like to point out that all of you use technology because you are tuning into this talk right now via the internet and computers and lots of things that require power. But also, I imagine that the vast majority of you use technology in the form of your science, especially in terms of things like telescopes that you're currently building or are using. Some of you may have even had the experience of needing to power down your instruments on your satellites in order to protect them from space weather. So the purpose of what we're doing with the project that I'm presenting here is really to improve our understanding of space weather and its impacts at Earth. And we're going to do that by looking inside the sun. I would also like to point out that we have pretty epic data images. So yeah, fun times. And now there we go. Okay, so this is just an example of a solar wind model. The key here is to note that this dot in the center is the sun. The inner boundary condition of this and many other solar wind models like it is the magnetic field of the sun. However, we only have half of the inner boundary conditions. I don't know if you'll realize this, but we can only see half of the sun at a time. So there's been lots of research, which I'm not going to go into here, about how you really need the global magnetic field in order to make reasonable estimates and especially near real-time estimates of what the space environment conditions are. And in order to be able to predict space weather as well. So can see here, Earth is this little dot here. There's a CME that's predicted to be passing through. It's going to narrowly avoid us, might hit some of these other spacecraft and planets. But yeah, so, and this is actually a prediction. So this is a few days in from now. This is the expectation. But again, it's only using half of the inner boundary condition. So now it's time to make you all helioseismology experts. For those of you who don't know what helioseismology is, it's seismology, but on the sun. So we're taking waves on the surface of the sun and watching how they interact with the magnetic field. So if you think about a lake and an island in the middle, waves hitting the island, it's going to perturb the waves, and you can study the structure of the island based on what the waves look like before and after. We're doing the same thing on the sun, but the lake is now a vast sea of plasma, and the island is a magnetic, the magnetic field. So this is just kind of to show you sort of what the data that we work with is like and what we can do with it. From near side observations, this is a Doppler image of the sun. So what you're seeing is velocities moving towards us and away from us in the plasma. If we zoom in on a section, you can kind of see that a little bit better. This first image here hasn't been filtered. This is just what that region looks like zoomed in, but we can use Fourier transforms to isolate which wave modes we're interested in looking at. We can look at all of the acoustic waves. We could isolate one of these acoustic waves if we wanted to. We can look at the F mode spectrum if we're interested, and then we can transform back and only be looking at those wave modes. Now, this is just for a more local region of the sun on the near side. And what we want to do is look at the far side of the sun. My slides are having trouble loading. Okay, so again, this is what I was just saying. It's basically perturbation theory. You look at waves incoming and outgoing, or moving through some sort of a object that's going to perturb them, and you look at what the expected wave travel time in theory should have been if that object wasn't there, and you look at the difference between that and what the actual observed wave travel time was. And depending on the wave mode, you can look at things much smaller features, like we would be here if I zoomed in on the into this image, or if you pick particularly large wave modes, you can actually look at things that bounce around the entire sun and can probe the side of the sun that is away from you. So that's pretty exciting, and that is the first thing that we've done. My images do not want to load. So this is a snapshot in time of so on the left side, it's the near side that we can observe directly from an Earth point of view. The right side is the far side of the sun that we do not have direct observations from at this point. There were two spacecraft that for really practically a period of 4 years, although it should have been 8, the stereo mission that did observe on the far side of the sun, but not the magnetic field. So they were observing in EUV. So we have comparison images for a single snapshot in time of both the near side AIA EUV wavelengths and the far side EUV wavelengths, near side magnetic field, far side acoustic maps. But the acoustic maps don't have any sort of magnetic field information. So then the question becomes, how do we take these maps and produce some sort of a magnetic flux measurement from them? And the answer, if all of my images will load, there's a lot on this slide, so bear with me. I'm going to skip a whole lot of details, so please feel free to come find me or any of my colleagues in this solar physics group and ask us questions on this. But the answer is machine learning, right? So basically what all of this is showing is so here's near side images at the top again from the satellite that whose data we work with, SDO, the Solar Dynamics Observatory. Again, we have the EUV and the magnetic flux images. I'm jumping the gun here. That are direct observations, and we have trained a machine learning algorithm to be able to take these EUV images and convert them into magnetic flux. There's been a lot of research that shows that this relationship is pretty strong and practical. So we felt confident doing this. And then once we train that machine learning algorithm, we can take the far side observations in EUV and convert those into far side magnetic flux from direct observations. Now, the problem is that we don't have these far side observations anymore. So all that gives us is 4 years of from 2010 to 2014, these far side magnetic flux maps, when we want something that will show us what the magnetic flux on the sun looks like now. So here comes the helioseismology. We take these Dopplerograms, we convert them into our far side flux maps, and then we train another machine learning algorithm between the far side acoustic maps and these far side magnetic flux maps, which then produces these far side magnetic flux maps that are based solely on the helioseismology. Okay, so the goal here is to use only near side Doppler velocity images in order to produce the far side magnetic flux, and we have done that.
We have about 30 seconds, Shay.
30 seconds. Okay, well, here's the crux of it. Doppler images that we can get of the sun produces magnetic far side flux. What we're doing now is trying to make it so that we can import these data into these solar wind models and be able to better predict the propagation of space weather and how it's going to affect you and your technology and your telescopes. And just real quick, last thing, shout out to Sinan and Ritu. We are organizing an eclipse event coming up in a month. Please join us. It's going to be awesome. And that's all I have to say.
Okay, thank you, Shay. I think we have time for one quick question, and if I can ask Christian to come down to the front and get a microphone while we do that. So any questions for Shay? Roger at the back. We're going to get a microphone.
I could not hear.
It's fascinating. I had no idea you could do this. This is great. Is one of the easier things to do with this, and none of it's easy, of course, to time when a flare happens on the back of the sun, so you can then correlate it with the space physics observations further out, so you can actually get the time, then suddenly there's a jog. And that must be a bit easier than doing the complete reconstruction.
So actually, that's a lot harder. We still don't entirely understand the physical mechanisms that produce flares, even on the near side of the sun. So being able to predict them on the far side of the sun makes it much more challenging. I am involved in a project. We actually had a summer student working on it this summer who, what they were doing was trying to look at the characteristics of the active regions that we're detecting on the far side of the sun, like the size, location, how fast they're growing, and correlating that to how flare productive they're going to be when they come around to the near side. So if we can develop something like that, that would be that would get us in the direction that you're talking about. But right now, predicting when a solar flare is going to occur is it's still pretty 50-50. The best prediction is what happened a minute ago. So if it didn't flare just now, it's not going to flare, and then it flares, and oh, so it's going to flare. Yeah, so that's still a hard problem.